So we're moving to sort of a different phase in our course, and now there's going to be less focus on coding and more focus on algorithm development. So your remaining tests are going to be on algorithm development, and I think that is a skill that you now need to learn, because for the first half of the course, we've been doing a fair bit of coding. We've been understanding how to code the basic data structures. And now that we understand that, it's time to go one level above and see how to use them to devise algorithms. So we're now going to start with what I'll say is the design and analysis of algorithms. So this is a common task that now, as a computer scientist, you will have to do, either in your upper division courses, or in interviews, or as a developer, or as someone who's designing algorithms somewhere. So what you have is given an algorithmic problem.
Session raise hard to bother
Yeah.
you, but
Oh.
could you also share?
You want me to? Yes, I will switch. Yeah, right.
Thank you.
There. Is that better?
Yes, thank you.
Okay. Yes. Given an algorithmic problem, and you are going to have to do this in your next two tests. You have two tasks. Write pseudocode for an algorithm solving the problem. Write or perform a big O runtime analysis. There's a third step here that you are not going to have to do as part of this course, but it typically ends up being something that is in 103 territory, something that is not as required of you if you were to be an applied person, but if you were to be more theoretical, then this would also be something you need to do, is to write a mathematical proof that the algorithm is correct. Now, as I said, I will talk a little bit about this, maybe in a few lectures, but this is not something that I'm going to expect you to do in this course, although it does become an important part of the mathematical analysis of algorithms. So let me start with a simple example, and we'll go from there. Okay, so here's an algorithmic problem, and by the end of today, I'm going to share with you a long list of algorithmic problems that you need to prepare for the next test. For every algorithmic problem, you need to be able to do steps 1 and 2. Okay, so what are the so let me give you an example. Given an array of, I'll say, positive integers, array A, determine if A has a Pythagorean triple. What is a Pythagorean triple? It's numbers A, B, and C, so that A squared plus B squared is equal to C squared. So for example, 3, 4, 5, 5, 12, 13, for example. Given an array of positive integers, you have to determine if A has a Pythagorean triple. That is the problem. You need to write pseudocode and you need to perform a runtime analysis. Now, there are lots of questions like this. What I want to teach you is the basic methodology to solve these problems. And if you follow this methodology, you will typically make substantial progress towards solving it, even if you don't come up with the best solution. What is that sort of methodology? So step 1, always, and I'm going to write this in big capital letters so that you remember, find a brute force solution. Find a brute force solution, and then do these. A brute force solution is a solution that typically only uses arrays, so no fancy data structures, and only uses linear search, and is usually a bunch of nested for loops. For any question that you come up with, the first thing you should do is to find the brute force solution and then write down the pseudocode for that and perform the analysis. Even in an interview, if you're in an interview, the first thing you do is to find the brute force solution and you explain the brute force solution. If you're sitting in front of an interviewer, or if you're sitting and discussing this with a bunch of people on a project, even if the brute force solution is trivial, you first start with that. You write it down and you say, this is the brute force solution. Now let's build on this. And then what you do in sort of step 2, which is the complicated part, is use a fancy data structure or divide and conquer, or sorting, or things like merge partition tricks, which are merging sorted arrays, partitioning an array. Use these to improve runtime. And this process is often, you keep going back and doing it. You keep trying to improve it, and you see how far you can get. Typically what this does is this converts O of n to an O of log n or O of 1. And I'll show you an example of that. So what you do is you'll start with a solution here, and maybe your solution here is going to be something like n cube. You're going to apply one of these methods, and the n cube is going to come down to n squared, or maybe n squared log n. Then you try it again, maybe you'll get it down to n log n. How long you have to keep going down this process, one doesn't know. For some problems, it's even a research level problem to find out what the best solution is. But typically after a few iterations of this, once you do a few improvements, you have a reasonably good solution. Okay, so I'm going to start with the brute force solution for this problem, which if you think about it is really, really easy. So let's write that down. So I'm just going to write it out as pseudocode. So I'll just say that the length of A is n. So what I can do is I can just do for I going from 0 to n minus 1, for j going from 0, or j going from I to n minus 1. We'll say for k going from maybe I plus 1, j plus 1 to n minus 1. Simple. You can just say check if ai squared plus aj squared equal to ak squared. Right, this would be the simple way to do it. And you can sort of check, you should technically check other permutations as well. You can check if this, or a k squared plus ai squared equal to aj squared, or ak squared plus aj squared equal to ai squared. And you can say that I can just say if this, then just return true. Or you could return ijk, and over here you return false. You can do this, with the braces, without the braces, whatever way you want to write clear pseudocode. When I give you a question of this form, or if you get a question of this form somewhere in the future, you write something like this down. Simple pseudocode. Okay? Then what you say is, this line over here runs in O of 1. This line over here, that's a for loop, so this runs in O of n. This is O of n square. And this is O of n cube. And you say the algorithm is a triple nested for loop where each loop runs at most n iterations. The innermost statement, and if you want, you can even number these. Line 1, 2, 3, 4, and 5. The innermost statement, step 4, runs in O of 1 time. Hence, the running time is O of n cube. Okay? In your tests, when you get a question of this form, this is what I expect. I will say, just write down a brute force solution, and this is what you need to write. Right? So this is the pseudocode of the algorithm. This is the runtime analysis. It's convenient to write the runtime of each statement by the side so that you can track it, and then this gives you your solution. If you get this in an interview question and this is what you do, then you will pass the basic test. And then they will check whether you can go further and improve it.
So your high resolution is down.
I'm sorry?
The high resolution is down.
The high resolution, oh, it's down. Hang on. Sorry, can you see it now?
Yep, we can see it now.
Okay. Okay, so this is what I expect of you. And I expect you should be able to do this for about 30 questions that I'm going to give you. Go ahead and do it. Do as many as you can. And this is going to be excellent practice for you. This is sort of the next stage of algorithm development. This is the design and analysis of algorithms. So if you were in a group and somehow you had to do this, you would write this down on the board. You'd say, this is my pseudocode, and here's my runtime analysis. Now let's see if we can do better. We can now think about it. But does this make sense? Any questions about this?
Is there any undergraduate classes that focus on this?
It's supposed to be this one.
Oh, well, like, you know how the step 3 is like running a mathematical proof that your algorithm would work. Is there anything that? Like,
so it's again, this is a longer story. This is supposed to be partly this course and partly 102. Previously, I used to devote longer times for the mathematical proofs, although I at some point realized that I think it's better to get up coding skills, better to strengthen coding skills than to strengthen proof skills, although both are important. But
at an interview, will we be expected to understand mathematical proofs as well?
no, I don't think anyone. No, not at the undergraduate level. No one is going to expect you to write a proof.
Professor,
Hmm?
when you're looking at nested for loops, is it always best to start like the bottom most nested for loop and go up like that?
Yeah,
Right.
because you're going to see that eventually this sort of statement, we might do something more complicated here, and that might not be O of 1, in which case it's going to change things. So it's better to start inwards and then go up.
Makes sense. Thank you.
Questions about this?
Sesh, let's say that wasn't O of 1, say it was O of n.
Mm-hmm.
Then you'd have O of n to the fourth at the top, right?
Exactly.
And if it was...
What you would write here...
What if it was log n?
Okay, so let's say this was log n.
Yeah.
So you're doing log n times, so that's going to be n log n. And you're doing n log n times, so it's n squared log n. And that n times, which is n cubed log n.
All right, that makes sense. Thanks so much.
So if I understand this correctly, you're multiplying like the runtime of step 4 with, or I guess the resource cost of step 4 with the other ones.
Exactly. It's because this line by itself runs an O of 1, but this for loop is running this line n times. So this for loop is going to take a total of O of n. This for loop, the j for loop, is running the k for loop n times. O of n times, at most n times. So it's O of n squared. The I for loop is running the j for loop at most O of n times, so it becomes n cubed.
Right. And if step 4 was n, then it would be n to the 4, right?
It would be n squared, n cubed, n to the fourth.
Okay. All right, that makes sense. Thank you.
Okay? So far, so good?
Can we improve on n cubed?
Good. So that's the next part. So I want to make sure that everybody understands the n cubed solution. This is what I call is the brute force solution. It's brute force because you're just like throwing for loops at it. Always get the brute force solution. And I have to repeat this over and over again when students come and try to do something complicated. Don't start complicated. Always start easy. Start with doing no fancy data structures, no divide and conquer, nothing. Now we have n cube. Once you have a brute force solution down, then you try to improve. So now how do we improve? The first question we ask is, what are our tools for improvement? Convert a linear search to a binary search. That's one tool, which is related to the sort the array. I'm just listing out a bunch of things. Use a better data structure. So let's start with using each of these. So what you do is you say, okay, there's n cube because you have a triple nested for loop. You say, let me look at the innermost one. How could I improve that? So now let's go back to this logic. So I'm going to write down this logic in a slightly different way, just so that it's simpler. And I want to have this on another page. Again, ignoring corner cases. So when you write pseudocode, you don't have to worry about the corner cases because you're just getting the overall logic. When you code, of course, you have to do the corner cases. Right now, at this level of granularity, let's just start by saying, okay, so for I going from 0 to n minus 1, and I'll say for j going from 0 to n minus 1. So maybe I and j are, if they're the same, then you can say, don't do it, or just go from I to n minus 1. That's not important. The point is, what we're doing is we're saying, well, what is this piece of logic doing? It's checking if I and j participate in a Pythagorean triple. It's checking if I and j participate in a Pythagorean triple. Right? And actually, if you technically look at this, sorry, let's keep that in there. Okay. So we're spending n cubed time already. So we can afford to sort. So let's just say, suppose A is sorted. So we can go ahead and do this in O of n log n, right? We could do this in n log n, which is anyway less than n cubed. So this isn't going to hurt us much. Does this process become easier in any way? Does this process become easier in any way?
Professor, could you repeat the question one more time?
Sure.
Please?
So let's just say that A is sorted. If the array was sorted, does this part become easier? Now, what is this part doing? Right? So what is this part doing? It says that you fix AI and AJ. Let's just say you fix AI square plus AJ square and find a K such that AI square plus AJ square is equal to AK square. And then you have these other conditions as well, which is AJ square minus AI square and others. But let's first start with this. So you find a K such that AI square plus AJ square is equal to AK square. Is this easier if the array is sorted?
So possibly because
Yeah.
the AK will be in the second half of the array.
Not necessarily.
Because it'll be more.
But that doesn't mean it's in the second half. It could be somewhere towards the beginning.
You wouldn't need to search through all the elements in the array because it being sorted. You would know that at most, like AI squared plus AJ squared is at like some value, right?
Right.
So you would not need to search through all possible elements in the array to find that value.
So what do you need to do?
Binary search.
Yeah, binary search.
You do binary search, right? What you're trying to do is you're trying to find this value. And you could do binary search. So this is linear search. Instead, you could do binary search. And so what you do is you convert an n into a log n by sorting the array. One of these inner things becomes log n. So let's go and look at that. So now I'll write this again. I'll say for I, so this is sort of step 1, going from 0 to n minus 1. Open that up, brace here. 2, say for j, going from I plus 1 to n minus 1. Okay. And what I'll do is I'll do a step 0, which is sort A. Right? So I sort A. Okay. So I sort A. Then I run a double for loop. Then in here, what I can do is using binary search, find an AK that is equal to the square root of AI square plus AJ square. And you can also do the other part, which is find AK is equal to square root of AI square minus AJ square, assuming AI is greater than or equal to AJ. I mean, otherwise you flip what I and J is. Otherwise you flip I and J. Like, if not, then you switch them. Or I'll say that, right? Or switch.
Follow your logic, then that wouldn't be possible since the array is sorted, right?
Good point. Yeah, you're right. So you don't even need this. Sorry. Because it's sorted, you don't even need this. Good point. Yeah. And that's it. And then here you can return false. And if you find, if you found, you return true. Sorry, this is a bit of a mess. Okay, now let's go ahead and write down the runtime. O of log n. That's for the binary search. How long is this going to take? This is going to take O of n log n. How long does the outermost one take? It takes O of n square log n. How much does the sorting take? It takes O of n log n. So technically, instead of calling this 2, 3, I should call this A. I'll just number it differently so that you see that they're nested, right? And so the running time is O of n log n plus O of n squared log n, which is just O of n squared log n. The running time is O of n log n plus O of n squared log n. N squared log n dominates the sort time, so it's n squared log n. Alright, so this is the way you go. You start with a brute force solution, you try to improve one part.
Professor, why is it added again, as opposed to like multiplying those two together?
Because you only sort once.
Oh, okay.
Right? Whereas these are nested.
I see.
So the runtime is now n squared log n. So you improve from n cubed to n squared log n. So at this point, so the first part, you cross the screening for the interview. At this part, you're probably going to get the job, right? And because you logically think through this process, you're not like randomly trying to solve this problem. You start with brute force, you observe where there is linear search, and you convert it to binary search. This takes practice, right? There's no way that you're going to do this just by listening to one lecture. That's why I'm giving you lots of problems, and you have to try all of them. But you try them in the systematic manner. Okay, n squared log n. Any questions
I have
about?
A question. So, so the sort you initially said to think of that. Well, that's not going to hurt us too bad because we're already n cubed, right? But when in the final big O in this, it completely disappears and isn't even factored in.
Yes.
So it's like it doesn't matter to add the sort.
In some sense,
time-wise.
In some sense, the time it takes for the searching is so much more than the sorting that you might as well do the sort. Right? The sorting time is dominated by the search time because you have to search through to a double nested for loop.
Right, and I think just to add to that, Rob, I think if you didn't sort it, it'd be impossible to do binary search, right?
Exactly. You wouldn't
that's why it's necessary to have that step.
So it's so.
Oh right. No, I get that. And yeah, you do have to do the sort to do the binary search. But I mean, as far as big O time, and Sesh probably knew this going in, that the search was just going to disappear from the big O time.
Yeah, the search disappears in the big O time. So again, I emphasize, I'm going to say this multiple times in this lecture and the next few lectures. You need to be able to do this when you have to do this either as part of your job or as part of an interview or as part of a course. You write down the pseudocode and you write down the analysis in a systematic way in this form. So we got from n cubed to n squared log n. Any questions about this? Because now we're going to try to go even better.
I guess kind of a quick question. I know this probably depends on the context, but like say in the interview environment, could we like say to what extent we would have to optimize the algorithm? Like at what point can we say this is an acceptable answer?
I think the interviewer will decide.
Okay.
Right, the interviewer will probably say, "Oh, can you do a little better?" That's an indication that you probably can, right? I mean, the interviewer is a human being, right? So they have a solution in mind, and they're trying to guide you until you get to that point. The thing is, if you don't give the brute force solution at the very get-go, then it's not clear that you've understood the problem. When you give the brute force solution, it shows that you comprehend the problem and at least you know how to solve it. Even in practice, writing down the brute force solution gives you a lot of clarity because it gives you a benchmark. And then you try to improve on that benchmark. If you don't do a brute force solution, you have no benchmark. You're shooting in the dark. Questions?
Professor,
Yeah.
can we do better than n squared log n for this question?
I'm sorry, say that again?
Can we do better than the big O of n squared log n?
Yeah, so that's where. So let's see, can we do any better than n squared log n? Okay, let's go. Now the question is, the binary search took log n. Now let's think, what we're really trying to do is trying to search in a list. Now what you do is you go through your list of data structures one by one and you see which of them is going to help you. Is a stack going to help you? No. A linked list? Not at all. Linked list is not going to help you. A stack? No. A queue? No. A heap? Well, a heap doesn't allow you to find. Okay, what about a balanced binary search tree? And say, okay, maybe that's going to help. But even in a balanced binary search tree, the search is still log n.
Use a hash table.
What about a hash table? Say, oh, okay. In a hash table, the searching is constant. The searching is constant. And you can build a hash table in linear time. So now what you do is, so step 0 would be insert A into a hash table. Step 1 is the for loop on I, the for loop on J, and then using the hash table, search for AK being, or search for, I shouldn't say AK, search for AI square plus AJ square. And you may also have to do the yeah, and you can also afford to sort. So you can also sort, because you'll see that the running time of this is O of 1, this is O of n, and this is O of n squared, and this is O of n. And so what you get is O of n plus O of n squared, O of n squared. Now I'm not writing down everything as I did before, but it's the same. You have to write all of those things down. The runtime is now O of n squared. So you got it down from n cubed to n squared log n to O of n squared. By, again, like this process of, I find a linear search, I do binary search, now I use a data structure. There is some, in some situations, this may not be an acceptable solution if they say get a solution with O of 1 or O of log n extra memory. In some situations, this would be a demand. You cannot build a hash table, and in that case, you cannot do this. So if you're not allowed to build a hash table, you cannot do the solution. But if you can build a hash table, then you get O of n squared. Is this clear?
I had a quick question. What kind of hash table would this be? Would this be a chain hash table, or the other kind?
Usually you don't have to say, because chaining and open addressing is under the hood. Just as if you say use a self-balancing binary search tree, you don't necessarily have to say AVL or red black. You can pick one of them. No one is going to ask you internal details of how you implemented that, because you assume that those are available as libraries now. Like in this, when you're doing algorithm development, you assume, okay, you have these data structures and now you get to use them. Does that make sense?
Yeah, that makes sense. Thank you.
This gives you O of n squared. Except, suppose you had to get a solution with O of 1 extra memory, as I will ask in my question. So suppose you cannot build a hash table, and that's because building a hash table requires extra memory. Then what do you do? Okay, so let me pause here. Any questions about this? Okay.
So at what point do you insert the items into a hash table? Is that before you enter the nested?
Exactly. So at the very beginning, you build a hash table with all the elements.
Okay.
Right? So you insert A into a hash table in the beginning.
Oh, and then you can do the square root of the sum of the squares and then just immediately go to where that's located.
Exactly. You just search for it in a hash table. The hash table will either say yes or no, right? Because a hash table can do a find.
Yeah.
And that's how it works.
Okay.
Okay?
So, Professor, you said that we couldn't build a hash table. So
Right.
would we possibly then build a binary search tree?
The binary search tree doesn't buy you anything because it goes back to n log n. Because essentially, a search in a balanced binary search tree is still log n. So it takes you back to n squared log n. So you don't even need to build a fancy data structure. Sorting helps. No, to get to n squared is tricky. But so okay. Now, this I'm just going to sketch. I'm not going to write the entire code. I'm going to draw pictures to show you what's going on. So getting O of n square without. Now you actually have to use a bunch of ideas. Now, because it's n squared, go ahead and sort. So you can always sort. So let's sort. Because that's just going to help us. That's just O of n log n. There are a few more ideas, remember. So the idea of merge and partition. And you try to use those. Now, this is not obvious. This is a pretty clever solution. What you do is the following. So let's say you sorted it. Okay, and I'm at I. Let's find Pythagorean triples where I is the min index. Because then we can loop over all I. So we're going to maintain 2 pointers. A head initially is I plus 1 and tail is initially n minus 1. So this is going to be head and this is going to be tail. Head and tail. So now check if A of I square plus A of head square is less than A of tail square. So let me see if this works out. No, so I think let me try to write this in a different way. All right. Let me talk about sort of a similar situation here. So this is where you kind of have to think about these things somewhat differently. Let me start at the other end. And so I is over here. I'll say let's find a triple where some A, so I'm going to refer to this as K, where AI square plus aj square is equal to ak square. So I need to find two things that are less than I. And now what I have is I have a head and a tail. And head is going to initially start at 0, and tail is going to start at k minus 1. Okay, so sorry, so ignore what I did earlier. So let's say a head square plus a tail square was more than ak square. Suppose. Then what should you do? So you're fixing k. Let's fix k. Right? So k is fixed. So imagine that you fix a k and you start with head and tail over here. If a head square plus a tail square is greater than ak square, does it make sense to move Sorry?
What?
Sorry, someone said
tail?
decrement tail. Because if you increase the head, it's only going to make the left hand side more, and you know that it's not going to work. Then you know that for any index, suppose this, then for any index greater than head, a of index square plus a of tail square is going to also be greater than a of square. This is because it's sorted. So this is the logic then, right? So you say if a of head square plus a of tail square is more than a of k square, then you decrement tail. If a of head square plus a of tail square is less than a of k square, then you increment head. Right, and if this is equal to a of k square, then we're done. Right, so this is essentially the same logic as partition, and what you'll see is that head is going to keep incrementing, tail is going to keep decrementing until eventually they bump into each other, and once they bump into each other, you're done. You know that there is no triple of this form, so then you go ahead and decrement k. Does the logic make sense? So when you fix a k, you can actually determine in linear time you can determine if such a triple exists.
And then we're just going to do that for all k.
You just do it for all k. This is a trickier solution, right? Where you kind of have to think outside the box to get here. And again, it's not completely out there because it's the same idea of partition, where you have these two pointers that are marching towards each other. And this idea of having multiple pointers that are sort of marching towards or away from each other is a very common trick. This is tricky. So I'm just going to write this out saying that for k going from n minus 1 to 0, so first is you sort a. It's like I call that step 0. For what we do is we initialize the head to be 0 and tail to be k minus 1, and I'll just say that use the logic above to find triple ai square plus aj square equal to ak square. And so this part is O of n. This gives you O of n square, and this is of course O of n log n. And so therefore you get back, it gets back to an O of n square solution. Okay, this is a trickier solution, so you know, it would be much to expect someone to come up with this on the fly. But the previous solutions, the n square log n is actually not that hard. So this is O of n log n, and now this is O of n square without a hash table.
Professor, when you decrement k, do you leave the head fixed in the same spot, or do you increment that by one?
No, you always, when you decrement k, then you reinitialize the head and the tail.
Okay.
Right, the head and the tail will always begin in this, and then they will march towards each other.
Okay, that makes,
Okay.
I see.
Right, so you always, so as I said, you initialize the head and the tail at the beginning when you reset k, and then you use the above logic.
So like in the next iteration, for the first time you decrement, then the head will advance one and the tail will go.
Head goes back to
one.
0. Head goes back to 0, tail goes to k minus 1.
Okay.
So
and then they continue to march towards each other.
they would march towards each other, they would bump into each other, then you decrement k, and then you reset the head and the tail.
Okay. All right.
That's why there's an initialized step here. Okay? Then you might ask, what about better than n squared? It seems like, okay, you could get n squared. Can you do better than n squared? And this is a huge open problem in theoretical computer science. Like, it's unknown. It's believed that you cannot do better than n squared. We don't have any proof. And this is a major open problem. In sort of math, I'll say TCS, where T is theoretical. And this is actually referred to as the 3-sum problem. Typically, it's phrased as follows, although it's essentially identical. It says that usually it says find I, J, K such that AI plus AJ plus AK sum up to 0. This is usually how the 3-sum problem is phrased, and it's identical to the Pythagorean triple. Like, it's just by moving things around. So you can very easily bump into something which is just unsolved, and you don't know. You might say, how do you even know that you're stuck at something that is unsolved? You know, that is challenging. But typically, again, you start with brute force. You'll be able to improve like an n factor, or often like an n log n factor from brute force. You can usually shave off, you can convert an n to a log n, and maybe you can convert to an n to O of 1 using data structures and various methods. So this lecture was to show you an example of how you would attack such a problem, how you would do such a problem. I will spend another lecture doing more such questions. What I will do is I'm going to give you, and I'll put this up on my website and explain on Piazza. I'm going to give you a list of about maybe 20-30 questions that I have curated over the years, which are good practice to do all of these questions, these types of problems. So, okay, any questions at this point?
Did you go back to the constraints on where you said a hash table couldn't be used?
Yes. Any questions? Okay, so this is it's sort of a classic problem of checking when 3 numbers sum up to 0. And so hopefully you now see the logic, you understand it. Go back and look at the solutions. Make sure that you understand the brute force solution and the n squared log n solution, because those are fairly easy. The other solution which does, and make sure that you understand getting O of n squared using a hash table. O of n squared without a hash table is also important, but get to that only when you finish all the others. Make sure that you're able to write the pseudocode and write down the runtime analysis the way I did for the very first in the very first problem, right? I wrote things out sort of in a fair amount of detail. This is the kind of answer that I will expect from you in the test. This is the kind of answer that I'm going to expect from you. I'm going to give you a problem and say, okay, write down pseudocode for an algorithm and write down the analysis, the runtime analysis.
So do we need to find, like, you to find theoretically the best solution, or we just like can find the? No,
I mean, what I will give you parameters of that. So actually, what I will usually say is, for full credit, just give me a brute force solution, but write it well.
Oh. Okay.
And for extra credit, if you can improve, then you get a little bit more.
Okay. So we don't need to find like the best solution.
No, I mean, I don't expect you to be able to do that in like, a half an hour, 1 hour test. And I'm giving you like a long list of curated questions, and I'm going to ask something from there.
Okay.
Wait, so this is for the last 2 exams?
This is for the last 2 tests, exactly.
Oh, okay. So the final will get an algorithm to analyze on graphs, and we write the brute force method.
Exactly. Yeah, their brute force is a little bit more complicated to do because you have to build a graph, but you'll get a graph problem. Again, what I'm checking is not whether you came up with the best possible solution, but rather, can you write down a basic solution cleanly and write down the analysis properly? And
and then we'll just have like about an hour to do that.
You'll have more than enough time. I mean, you would have realized by now that the tests, if you've prepared well, don't really take that long.
Yeah, definitely not.
Think of it as, this is my way to force you to do more problems than I can afford to grade. Right? So that's basically the parameters of the test.
Wait, so Professor,